Okay, welcome to Chapter 13, Section 4, Conservation of Energies. Let's get right down to it. Here's the key ideas. So, how does energy change? What is the law of conservation of energy? How much of the work done by a machine is actually useful work? Alright, so let's move right on in here. How does energy change? Energy readily changes from one form to another. Potential energy, like we talked about in the last section, can become kinetic energy and vice versa. Example, as a roller coaster car goes down a hill, potential energy changes to kinetic energy. You've been on a roller coaster, you know you go to the top of the hill, it kind of goes slow. As you come down the hill, it gains speed. Your potential energy, because it's based on height, is going down because you're moving closer to the earth, so your potential energy is reducing. As you come down, you're speeding up, so your kinetic energy based on motion or velocity is increasing. Kinetic energy can also become potential. So example, kinetic energy of a roller coaster at the bottom of the hill can do work to carry it back up another hill. So you get to the bottom, you're going fast, and as you go back up another hill, you lose speed because it's being transferred into potential energy or gain in height as you go up the hill there. Mechanical energy can change to other forms of energy. So graphing skills here. Let's look at graphing mechanical energy. Basically just kinetic energy and potential energy. So in section A here, bar graph shown here represents data of a roller coaster car. What variables are plotted? Identify the independent and dependent and independent variables. What does this legend tell you about this graph here? So location. The location is the independent variable, and the mechanical energy, which is the total energy, both of kinetic and potential, is the dependent. It depends on the location you're at. So let's look at location B here, or A. Excuse me. On location A, you have all potential energy, no kinetic energy. So since it has no kinetic energy, it means the object, or the roller coaster in this case, is not moving. So we're going to guess if it's not moving, it's probably, and it has a lot of potential here, we're going to probably guess it's at the top of a hill. Position B. Potential energy has gone down, but kinetic energy has increased here a little bit. We've got some of the blue showing. So it means it's moving now, but because potential energy is less, it means the mass of the roller coaster didn't change. The gravitational free fall acceleration didn't change. So the only thing that could have changed is the height. So it looks like we're coming down in height, maybe going down a hill. As we go down a hill from a roller coaster, you know, we're gaining speed there. If we're gaining speed, that means we're gaining kinetic energy. And then at location C here, we got all kinetic energy, which means it's moving and has no potential energy, so the height must be at 0. So we must be at the bottom of a hill here because it's got all kinetic and no potential. And then in section D here, or location D, it's got about halfway. So it looks like maybe it's halfway up the next hill because it's got some potential energy and some kinetic energy. And actually they're equal. Looks like they're split almost in half there. So maybe it's gone like halfway up the next hill there. So that's what we can interpret by looking at this bar graph of both potential and kinetic energy. And notice that the total mechanical energy stays the same all the way across. The energy is the same all the way through. It's just a matter of whether it's getting transferred in from potential into kinetic or kinetic back into potential. So moving on here, study the axes and legend determine the variables. So the location is the variable on the x-axis. Two variables are plotted on the y-axis, kinetic and potential energy. So we've kind of already done that. Relationship between the variables, the independent variable is location. We figured that out, and the the total mechanical energy is the dependent variable. But because the car's kinetic energy and potential energy change with location, so these change depending on the location. That's why it's the independent variable. Let's see, legends indicate that the car's mechanical energy consists of both kinetic and potential. So, yep, it's got kinetic and potential there. So, alright, let's move along here. We're going to talk and watch this visual concept on energy conservation in automobile engines.
An automobile engine converts the energy stored in chemical compounds into mechanical energy that can make the car move. Here is a cutaway drawing of one of the combustion chambers in an automobile engine. The piston begins to move downward as the intake valve opens. The partial vacuum created by the piston allows a mixture of fuel and air to enter the combustion chamber. When the piston reaches the bottom, the intake valve closes and kinetic energy stored in the flywheel and crankshaft drive the piston up, compressing the fuel and air mixture. Just before the piston reaches the top, an electric spark from the spark plug ignites the mixture. As the fuel-air mixture burns, the temperature of the gases in the piston increases, which causes the pressure of the gases to increase also. The increased pressure pushes the piston downward. Chemical energy is converted to thermal energy of the gases and then to kinetic energy of the piston. As the piston reaches the bottom of the cylinder, kinetic energy of the rotating crankshaft drives the piston upward again, forcing the burned gases out of the cylinder. When the piston reaches the top, the exhaust valve closes, the intake valve opens, and the cycle starts again.
Alright, so let's move on here. Law of conservation of energy. What is the law of conservation of energy? Well, energy cannot be created or destroyed. So in other words, total amount of energy in the universe never changes, although energy may change from one form to another or be transferred from one object to another. So let's look at this video on conservation of mechanical energy.
Imagine an enormous steel ball resting at the top of a roller coaster track. If the track and the ball are perfectly smooth, then no energy will be lost due to friction as the ball rolls along the track. We will also assume that wind resistance can be ignored. Since there is no friction and no wind resistance, the ball is not losing mechanical energy. Its total energy at all times will be the same. The energy can, however, change form from kinetic energy to potential energy. Without friction or resistance removing energy from the ball could continue forever on a closed track.
Alright, so let's move along here. Law of conservation of energy continued. Energy does not appear or disappear. Whenever the total energy in a system increases, it must be due to energy that enters the system from an external source. Thermodynamics describes the energy conservation. For any system, net change in energy equals the energy transferred as work and as heat. So if you lose energy out of a system, it's either done by work or by loss as heat from the system. This form of the law of energy conservation is called first law of thermodynamics. So systems may be open, closed, or isolated. An open system is energy and matter are exchanged with their surroundings. Closed system is energy but not matter is exchanged. In an isolated system, neither energy nor matter is exchanged. Most real-world systems are open, where energy and matter are exchanged with the surroundings. So efficiency. How much of the work done by a machine is actually useful work? How much are we really getting out of it? Only a portion of the work done by any machine is actually useful work. That is, work that the machine is designed or intended to do. So, not all the work done is useful work, and because of friction, generally work output is less than the work input. So efficiency is the ratio of the useful work out to useful work put into it. So efficiency is a quantity, usually expressed as a percentage, that measures the ratio of useful work out to work in. So your equation is efficiency is equal to useful work output divided by work input. So let's do a sample problem here. A sailor uses a rope and an old squeaky pulley to raise a sail that weighs 140 newtons. I think the squeaky pulley there, the word squeaky was put in there to say we're probably going to have some friction. It's not going to move real well. So he finds that he must do 180 joules of work on the rope to raise the sail by 1 meter. he does 140 joules of work on the sail. What is the efficiency of the pulley? Express your answer as a percentage. So the work that he did is the 180 joules of work. But he only raised the sail 1 meter, which means that the output work done by that pulley was just moving that 140 newton sail 1 meter. So if you calculate work, force times distance, that's 140 times 1 meter. The output work done was only 140 joules of work. So let's do the given and unknown values here. So the work input that the person did, the sailor did, was 180 joules he put into it. But what he got out was that the pulley raised the 140 newton sail by 1 meter. So the useful work out is 140 joules. So we need to find what the efficiency is. So we write the equation, insert the known values. The output work was 140 joules, the input work was 180. So we have an efficiency of 0.78, which is basically, as a percentage, you multiply it by 100, add the percent sign, so that would be 78%. Alright, so let's watch this visual here on mechanical efficiency.
The mechanical efficiency of a machine compares the amount of work energy output by the machine to the amount of work energy input into the machine. In the case shown here, energy is put into the system by the force that moves the block up the incline. As a result, the block gains gravitational potential energy. This is the output work of the machine. Mechanical efficiency can be calculated using the equation shown here, where W out is the energy gained by the object and W in is the energy put into the system. In a frictionless system, the energy gained by the object would be equal to the energy put into the system, and the efficiency would be equal to 1. In real-world machines, however, there is always energy lost to friction, so the efficiency is always less than 1.
Okay, so real-world applications, you're never ever going to get a machine that is 100% or